My dear students, let me welcome you all to a new edition of physics. As a matter of fact, classical physics failed to explain blackbody radiations. Theories of classical physics are good fit for the radiation of the blackbody at long wavelengths, but they fail to explain why the intensity of radiation fall rapidly at very high frequencies at short wavelengths, like ultraviolet region. They called this ultraviolet catastrophe because they couldn't understand why, but Max Planck managed to explain it. To know how he managed to explain it, stay with me and let's get started. Wave-particle duality. Wave-particle duality. As I said, we'll start with the catastrophe, ultraviolet catastrophe, or black body radiation. First of all, we need to define black body. So, talking about black body radiation. What about a perfectly black body? A perfectly black body is the body which absorbs all of the radiant energy falling on it and reflects none. So the definition is, it is an excellent absorber, an excellent, emitter. It is the body which absorbs all of the radiant energy falling on it and reflects none. So let me tell you something very interesting. A perfectly black body, you cannot see it. Why you cannot see it? It's very interesting because I cannot see anything unless it reflects light. And according to this definition, it is the body which absorbs all of the radiant energy falling on it and reflects none. So yes, we cannot find this perfectly black body. Okay, anyhow, it is an excellent absorber of radiant energy as well as an excellent radiator. A black body is considered an enclosure, closed thing from which no energy can escape once it has been received by it. Okay, we've got important hints here, concerning black body, and your attention please. When a black body is receiving energy, how? When it is surrounded by hotter objects. When a black body is receiving energy from hotter surroundings, it will heat up quicker than any other body of the same surface area. This is very important piece of information. Let me say it again. When a black body is receiving energy from hotter surroundings, it will heat up quicker than any other body of the same surface area. And we've got another piece of information. When a black body is emitting energy, and this happens when it is surrounded by, cooler objects. When a black body is emitting energy to cooler surroundings, it will cool down quicker than any other body of the same surface area. So excellent absorber, and excellent absorber when receiving energy, and excellent emitter when giving energy. Okay. Still talking about a perfectly black body. A perfectly black body emits, this is very important piece of information. It emits a continuous spectrum of radiation. Continuous spectrum means it has wide range of frequencies. A perfectly black body emits a continuous spectrum of radiation. That is to say, the radiation emitted by a heated black body has a wide range of frequencies. Okay, it is a continuous spectrum. And a continuous spectrum does not depend on the object. It depends only on the temperature. Okay. The radiation of the black body, which affects the eye, that can be seen by the human eye, as light extends roughly from 400 nanometer to 800 nanometer. To convert nanometer into meter, it is multiplied, yes, times 10 to the power of -9. So you can see, yes, the radiations which, yes, extends from 400 nanometer to 800 nanometer. This is the visible spectrum. Okay. When the black body is made hotter, its radiation becomes not only more intense, but something interesting, okay, will happen. For example, if you watch the filament of a lamp, okay, how to read the temperature of the filament of a lamp? By increasing the current flowing through it. As the current through it is gradually increased, okay, you will see it. You'll see the filament begin to glow deep dull red. It will start with red, become orange yellow, and eventually appear white. This happens when we raise the temperature of any black body. It starts when it's starting glowing, it will give a dull red, then by raising the temperature becomes orange yellow and eventually appear, yes, white hot. It will glow a deep dull red, become orange yellow once again, and eventually appear white hot. It has gone from warm to red hot and to white hot as temperature increases. In front of you, we've got something. We'll start now explaining. We've got the intensity, radiation intensity. Radiation of the black body intensity means the number of photons that fall per second per unit area versus wavelength measured in nanometer. Okay? What about these graphs? Each graph is, is obtained at a certain temperature. We'll start with temperature for 1000 Kelvin, then we'll raise the temperature. Your attention, please. Okay? So what about the figure shown in front of you? It is the relation between intensity of radiation and wavelength. Okay, pay attention to the region ultraviolet, because the radiation of the black body, since the classical physics couldn't explain it, we call it ultraviolet catastrophe. Okay? How? Some important facts that can be deduced from the previous curves. We'll take it one by one. First of all, the area between any curve. The area, yes, extending between the curve and the x-axis, the wavelength axis, gives the total energy emitted by the black body at that temperature. So, when you look at temperature 4000, the area between this curve and the x-axis gives the total energy emitted. At 5000, the area increases, means the emitted energy will be increased. Okay, but something very important. Look at the wavelength at which most of the intensity is radiated, peak wavelength. Okay? What happens to the peak wavelength? Most of the radiation emitted of the black body falls at a certain region. Okay, what happens to this wavelength? This is very important, and this is the problem that classical physics could not explain. So once again, the area between any curve and the wavelength axis gives the total energy emitted from the black body at that temperature, of course. Okay, the curves at lower temperatures, the curves at lower temperature lie completely inside those of higher temperatures. Okay, this indicates, yes, the total energy emitted will be increased as the temperature will be increased. The peaks, this is the important, the maxima of the curves tend to move towards shorter wavelengths at higher temperature. Okay, your attention. When the temperature is 4000 Kelvin, lambda maximum, yes, lies somewhere between 500 nanometer and 1000. When the temperature is raised to 5000, okay, the peak is shifted towards the left. Okay, when the temperature is raised to 6000 Kelvin, yes, it gradually, okay, moving to the left. So the maxima peaks of the curves tend to move towards short wavelengths at higher temperature. So we've got an inverse relation between maximum wavelengths and absolute temperature, and this is called Wien's law. So once again, to explain it, I know it takes time to understand it. So we've got the wavelength axis, and it is ranging from 0, 500 nanometer, 1000, and so on. Okay, as the temperature rises, the intensity of every wavelength increases. How do you know this? The area under the curve will be increased. Pay attention to the peak wavelength at 4000. Okay, peak wavelength, it means the wavelength at which the intensity is a maximum. Okay, at 5000 Kelvin, the peak is moved towards the left, shifts towards shorter wavelength. Okay, and at 6000, yes, it gradually moves to the left. So this is quite clear now. This is the peak wavelength. Okay, and we'll never obtain a peak at ultraviolet. This is the problem. Let me remind you with something. Classical physics are good fit at longer wavelengths, but at short wavelengths they cannot explain it. Why we cannot obtain a peak at ultraviolet region? This is the problem that Max Planck managed to explain. This is ultraviolet region. This is the visible. Okay, your attention. We cannot, by raising the temperature, obtain, yes, a peak wavelength at ultraviolet. This is infrared. Once again, intensities of the shorter wavelengths increase more rapidly by raising the temperature. Accordingly, an increase of temperature causes not only an increase in the total radiation, but also, this is the very important thing you should bear into your mind, but also shifts the peak of radiation curve toward the shorter wavelengths. Wien's law displacement. Wien's displacement law. What about Wien's displacement law? It says, statement of the law, the product of the wavelength at which the intensity is maximum, lambda maximum. Okay, what about the product? The product of lambda maximum and absolute temperature, and the absolute temperature of the radiating body is constant. So we've got an inverse relation. We can say lambda maximum 1 over lambda maximum 2 equals T2 over T1. It is an inverse relation. Your attention, please. Please note, here we've got two black bodies. One of them is the Earth and the other is the Sun. But temperature of the Sun is much higher than that of the Earth. So the peak wavelength, lambda maximum, of the Earth lies in infrared, in longer wavelength, as we said, as we raise the temperature, the maximum wavelength is shifted towards the left. Okay, so lambda maximum of the sun, yes, lies in the visible spectrum. Yes, its wavelength is equal to 0.499 micrometer, but lambda maximum of the Earth is 9.66, yes, micrometer. So once again, the temperature of the surface of the sun is 6,000 Kelvin. So its peak wavelength, lambda maximum, is about 5,000 angstrom, 500 nanometer. This was about the maximum wavelength, or lambda maximum, the peak wavelength of the radiation of the sun. Temperature of the sun is equal to 6,000 Kelvin. And radiation of the sun, most of it lies in the visible region. Almost 40% of the total energy emitted by the sun is in the visible region. 40% is in the visible region. And about 50 of it is in infrared radiation, and the rest is distributed over the remaining spectrum. And what about the radiation of the Earth? The Earth, yes, compared to the sun, it's not a glowing object, which temperature is far less than that of the sun. So peak wavelength lambda maximum lies in infrared, yes, region, not in the visible like the sun. And now, explanation of Planck's body radiation. The equations, as I said, of classical physics were a good fit to the black body spectrum at long wavelengths, but didn't work for short wavelengths. Short wavelengths like ultraviolet. So they called it, classical physics, they called this ultraviolet catastrophe. According to the assumptions of classical physics, yes, the intensity of radiation should increase as frequency increases. Let me say it again. The intensity of radiation should increase as wavelength decrease. Frequency increases means wavelength decreases. But in reality, it falls rapidly at shorter wavelengths. Okay. Planck's explanation of black body radiation. Yes, we want to know how Max Planck managed to explain this problem. Okay. The radiation of the black body are composed of billions of quanta or photons. Radiation are composed of quanta. Each quantum is a discrete amount of energy. So he proposed something very new, which is energy is quantized. Each quantum is a discrete amount of energy. You cannot have any value of energy, and okay, it is quantized. It has a discrete amount. Okay, each quantum is a discrete amount of energy. The energy of the photon is proportional to its frequency. Okay, energy of a photon equals a constant, Planck's constant, denoted by h, and nu is the frequency. Okay, so we've got something very important. Energy is quantized. Okay, or radiation are composed of photons. Each photon is a discrete amount of energy. Energy of the photon depends on its frequency. Okay. The photon has mass and momentum. Photon has mass and momentum. Electrons are called oscillators. Electrons of the atoms of the black body are responsible for radiating these photons as follows. Electrons revolving around the nucleus can only occupy certain set of allowable energy levels. Electron does not radiate when it is in one of the allowable energy levels. To radiate a photon, an electron should make transition. So, to radiate a photon, for an electron to radiate energy, to radiate a photon, an electron should make transition from higher energy level to a lower energy level, from E2 to E1. That the energy gained or lost, this is the most important piece of information. Energy gained or lost, what about this energy, is quantized. Okay. Energies of electrons are not continuous, but quantized energies. Energy of an electron is given from the expression E capital equals NH nu. H is Planck's constant. N is an integer. It could be 0, 1, 2, 3, 4. Okay, but not any number in between, any fraction, and this is the quantization of energy. Okay, we've got important hint here. The curves that represent the intensities of radiation emitted by different wavelengths, yes, what about them, by a black body at different temperature, support the particle model of light. Modern physics, we call it the particle model of light. Okay, now we've got something very interesting. It is thermal remote sensing. What about thermal remote sensing? Thermal remote sensing is the detection of infrared radiation emitted from a black body. So thermal remote sensing is the detection of infrared radiation. Okay, thermal remote sensing has very important uses. It is used in, and it is the detection of infrared. In mapping and photographing the surface of the Earth by satellites or airborne and terrestrial equipments. Yes, it can be used in certain military purposes, such as detecting and imaging moving objects in the dark at night by night glasses. We call this night visions. Yes, it can be used in medicine, in topography, tumor detection, and embryology. Also in criminology, and this is very important and is interesting piece of information. The heat radiated by a person, lingers for a while in a place even after the person leaves that place. And finally, spotting areas of high heat loss from buildings and detecting hot spots, and detecting hot spots in power cables. Now we've got a problem. Let's try to solve a problem on black bodies. A black body at 2000 Kelvin emits radiation with peak wavelength 1000 to 150 nanometer. Use this result to calculate the surface, the temperature of the star Sirius if lambda maximum for it is 71 nanometer, assuming that Sirius behaves like a black body. Okay, what is the rule to be used? As a matter of fact, I just mentioned one principle, one rule, one law, Vane's displacement law. We've got an inverse relation between peak wavelength and absolute temperature. So lambda maximum 1 T1 equals lambda maximum 2 T2. Okay, so 1250 times 2000. Okay, and what about the star? Its peak wavelength is 71, so we want its absolute temperature. It's all easy. It will be, yes, 35,200 Kelvin. Another problem, and it is by using the curves of the Sun and the Earth. You can use them to know lambda maximum of the Sun. It is 0.499 micrometer, and peak wavelength of the Earth, peak wavelength of the radiation of the Earth, it is 9.66 micrometer. Okay. What about the problem? The figure showed the curves that represent the intensities of the radiations emitted by the Sun and the Earth at different wavelengths. If the temperature at the surface of the Sun is 6,000 Kelvin, calculate the average temperature of the Earth. Okay, we'll do the same now between the Sun and the Earth. Okay, we'll use Vane's displacement law, the inverse relation between peak wavelength and temperature, absolute temperature of course. Lambda maximum 1 T1 equals lambda maximum 2 T2. So 0.499 times 6,000. 6,000 is the temperature of the surface of the Sun. Okay, peak wavelength of the Earth 9.66. So temperature of the Earth on Kelvin scale will be, yes, 309.93 Kelvin. In Celsius it will be 37 Celsius. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all.